Good morning, everyone, and welcome to third day of Epistemic Conference. It gives me a great pleasure to have with us Professor Vicente Talanquer from University of Arizona, Department of Chemistry and Biochemistry with us. He really wanted to come over, but due to other commitments, he couldn't come physically, but he's able to find time to join online. And we really hope that he'll be with us in some of our future events. I'll take a minute to say a brief introduction of Professor Talanquer. Professor Talanquer did his bachelor's and master's in chemistry at Universidad Nacional Autónoma de Mexico, shortly called as UNAM, and further joined for a PhD in chemistry at the same university. His PhD area was bulk and interfacial properties of reacting and associating system, and he worked with Professor Alberto Robledo, a prominent physical chemist. He then joined the same department as a faculty member, where he served till the year 2000. And in 2000, he moved to Department of Chemistry and Biochemistry at the University of Arizona in USA, where today he's serving as a university distinguished professor. He has been an active researcher in interfacial chemistry, along with a prolific research career in chemistry education, where he focuses on understanding reasoning strategies of students, particularly in problems that require qualitative reasoning, and then how these students' reasoning strategies evolve as the students grow academically. He also works on investigating teachers' thinking and decision-making strategies. Professor Talanquer has developed an innovative curriculum on development of chemical thinking, and also several resources on chemical thinking, but also systems approach for chemistry, which is becoming very prominent globally. I mean, it's catching attention, particularly for sustainability education. And while located in the realm of domain of chemistry, he has developed teaching resources on topics as diverse as antibiotic resistance to plastic problem and surfactants. So trying to really take chemistry out to many real-life challenges and areas which are not typically taught in general chemistry. The chemical thinking curriculum has also been highlighted and celebrated in multiple fora at the United States, and we are also drawing a lot of inspiration from some of the resources he has developed. He has served as chair of Chemical Education Division of American Chemical Society and has been on editorial and advisory board of several journals in chemistry, as well as in chemistry education. He has won several academic excellence awards right from his students' days at UNAM, and later several awards for excellence in teaching at University of Arizona. In year 2021, he received the ACS Award for Achievement in Research for the teaching and learning of chemistry. Of course, this nowhere completes the list of his accomplishments. Without taking further time, I'd like to invite him for the talk today. He's going to be talking on the topic investigating student reasoning to achieve our educational goal. I invite Professor Talanquer and request him to please start the session. We'll take questions towards the end of the session, and please raise your hands and we'll come to you. Okay, Professor Talanquer.
Great. Thank you very much for the introduction and also for the invitation to participate in your event. I wish I could be there. Just to give you a sense of where I am, I'm located in the state of Arizona in the United States, very close to the border with Mexico. That is where I come from originally. This area is called the Sonoran Desert. The university is a public university, and we have around 40,000 students working as graduate or undergraduate students. Since I joined the University of Arizona in the year 2000, so 25 years ago, I've been focusing my work on doing research in chemistry education. So in that sense, I would consider myself what people call discipline-based education researcher. And we have also been trying to use the results of our research and the research of others to develop educational approaches that we hope will improve student reasoning and academic performance in chemistry. I do not know the educational system in India, unfortunately, but just to give you a sense, typically we do our research with college students, and we typically work in very large classrooms. We teach courses that are over 200 students. So we try to develop educational approaches that can be implemented in these very large courses. And most of my career have been focused on doing research in what we call foundational courses. That is typically in the United States, the general chemistry and the organic chemistry courses for all types of science and engineering majors. What I'm planning to do with my talk is I thought that given the nature of my understanding of the focus of your conference, I thought that maybe you would be interested in seeing the type of research that we have been doing over the past 20 years in the area of chemistry education, and then show you how we have been using the results of those research the studies, also with the results from other investigators, to enact educational reform, particularly in general chemistry at our institution. So I will try to show how we have moved from research to practice and back and forth. So let me start with kind of describing the area in which we conduct research and the motivations to do the type of research that we do. I believe, based on my understanding of what is happening in the United States and in other parts of the world, is that science education in the past 20 years has seek to foster educational practices that are, I would describe, ambitious, responsive, responsible, and inclusive. So what I mean by that is ambitious teaching. We understand it as the goal is to sustain high and continuous levels of interest and cognitive demand in our classes. Responsive in the sense that we should be attentive and adaptive to the students' ideas, their abilities, and interest. Responsible because we should be teaching things that are going to be useful for the population of students that we work and the citizens that we want to prepare. And inclusive because we should create equitable learning environments that responds to the diversity of backgrounds, needs, and abilities of the students that we work. So now, from my perspective, this is pretty ambitious, and it requires a lot of understanding of what is happening in classrooms to better support student learning. Additionally, we have not only changed or developed very high goals for the type of science education or mathematics educations that we want to enact. We have also changed our educational targets. For many years, at least in the US, the focus has been on developing content knowledge and practical skills, typically in a not very well integrated way. And nowadays, our educational targets are much more complex again. So we see the need for focusing our courses on central ideas that are in each discipline may be different, but that can be used to understand complex problems across different disciplines. We want our students to understand how science is done and to participate and enact science practices. We want our students to be able to transfer their knowledge in a given discipline to other disciplines. And in that sense, we have this goal that we would like our students to understand the ways of knowing in our different disciplines. But we also want our students to develop different ways of thinking. In our case, for example, mechanistic reasoning, systems thinking, but now people are talking about other types of thinking like futures thinking, creative thinking. We also want our students to develop ways of working, learning to communicate their ideas, collaborate with others, be flexible and adaptable to the changing world in which we live. And we also want our students to become good citizens that are able to make decisions and participate in actions that support, for example, sustainable development. So in my perspective, we are expecting to create learning experiences that are very rich, that are very complex to enact in classrooms. And from that perspective, I think that we cannot go into classrooms without understanding what is going on with the student learning and what are the best practices that we could use to advance their understanding. So from this perspective, discipline-based educational research is critically needed to generate the insights on learning and teaching so that we can better understand the challenges that the students face and how we can best address them. Now, in that sense, my contribution, the contribution of my research group is small. No, it has been focusing on a certain area of these very ambitious goals. And what we have been trying to do in the past 20 years is to better understand how novices and experts reason in chemistry. So how they build inferences, how they make decisions, how they construct rationales, and by that I mean how do they develop explanations, how do they engage in argument, how do they build justifications, and the basic justification is that we believe that if we understand how novices reason and how expert reason, and we understand the difference between those, the gap that exists between those two ways of thinking, that we will be in a better position to help students close the gap as they progress in their studies in chemistry. Now, I understand that not all of you are in chemistry or are chemistry educators, so I would like to tell you a little bit about how chemistry education is typically conceptualized, particularly among chemistry educators. So it is very common in chemistry to talk about this important connection that we would like our students to make between the world in which we live, that we call the macroscopic world, and the submicroscopic world, that is the model work that the chemists have developed to better understand, to make sense of the macroscopic world. And we also typically say that chemists have developed not only models to build this ability to make sense of the macroscopic world, but they have also developed a very sophisticated representational system, a big and very complex representational or symbolic system that allows to connect these models with the real systems we are interested in. Now, this what is called the chemistry triplet has become what I would call a very powerful didactic model to guide chemistry education. But I have been claiming for many years that this is just I would say the surface of the iceberg. That in reality the major challenge for chemistry educators is to understand how we can develop what we call mechanistic reasoning that allows students and everybody, experts and novices, to connect the models that we use about the composition and structure of the systems that we are interested in with the behaviors of the substances in our world. And that this mechanistic reasoning is what allows chemists and scientists in general to make sense of the systems of interest. So this is, in this sense, this describes part of our interest in chemistry education research has been to try to figure out what do we mean by mechanistic reasoning in chemistry and what challenges the students face to engage in mechanistic reasoning, and how can we best support the development of mechanistic reasoning. More recently, we have also collaborated with people that think that this view of chemistry is a little bit constrained or a lot constrained, and that chemists also should be interested in understanding how the substances in the macroscopic world and the chemical processes in the macroscopic world are affecting the very complex issues that we are facing at a global scale. And from that perspective, if we want to understand how in chemistry, chemical processes, chemical products affect our daily lives at a global scale, that we need to engage in a different type of reasoning. And that's what this idea of also helping students develop systems thinking is critically important. and that also we may have to help them learn a different type of representational system, that allows them to think in terms of systems. So, and the goal in this case goes beyond helping students to make sense of what is going on in their daily lives, but to engage in what we call sustainable decision making and action. That is, understanding chemistry with the goal of becoming citizens that can participate in helping develop sustainable societies. So my research for the past since I started actually my career in chemistry education, has been focused on understanding what is going on in this side of this representation. That means how we define mechanistic reasoning in chemistry, how do we define systems thinking in chemistry, how experts engage in this type of reasonings, what challenges the students face to engage in this type of reasoning, and how we can best support the development of this type of skills in classrooms. Now, just briefly, because I will be talking about them, I would like to define how I understand mechanistic reasoning and systems thinking. So in general, mechanistic reasoning, the way we contextualize them is reasoning that allows to understand the properties and behaviors of a target system by building a model, typically at a different level or at a different scale, in which there are model entities that have certain properties that engage in certain activities, an organization, and then the task of the mechanistic reasoner is to build causal stories that connect the behaviors in the model system to the properties and behaviors in the target system. So in general, this is how we conceptualize mechanistic reasoning in our research, and we try to understand what challenges the students face to build this type of causal stories, and also, of course, to use the models of chemistry to engage in this type of reasoning. More recently, we have also been trying to better understand what we mean by engaging in systems thinking in chemistry. Recently, we wrote a paper in which we tried to conceptualize how we see, because there are different conceptualizations of systems thinking in different disciplines. But in the case of chemistry, we claim that if we want our students to develop systems thinking, they need to be able to develop 4 major skills: the ability to look at complex systems and identify their boundaries, the relevant components, and characterizing their properties at different levels of granularity or scales; that they should be able to identify and explore the interactions between the components of the system, how they engage in different dynamic relationships over time and space; that then they should be able to infer how, based on these interactions, how emerging properties, so how properties emerge from these dynamic interactions; and finally, that they should be able to use this knowledge to see how the system of interest interacts with other systems that could be systems that are working at an environmental level, at a social level, or at an economic level. So what I would like to do now is to tell you a little bit what we have learned through our research about the challenges that the students face to engage in this type of reasoning in our traditional chemistry classrooms, because most of the research that we have conducted has been conducted in traditional chemistry classrooms, many of them at the college level, some of them, a few of them at the secondary level in the United States. So what is that we have learned through our research? So in general, I thought that I wanted to summarize that most of our research indicates that it doesn't matter if we are talking about mechanistic reasoning or systems thinking, we are talking about simple chemical systems or complex chemical systems. The reality is that we have found that most of the challenges that our students face has to do with their intuitive and implicit ways of thinking. And I'm going to talk about 2 major pieces of intuitive knowledge that are very powerful in guiding students' thinking, and we can leverage to foster their understanding, but they also can constrain students' thinking in different contexts. So I'm going to divide this second part of my talk in try to tell you what we have learned about these two main areas of intuitive thinking that I characterize as having intuitive assumptions and then engaging in a heuristic reasoning. So what is that we have found? Well, our research indicates that in many occasions, the first way in which students engage in the analysis of, as I said, complex or simple systems is based on common sense assumptions about the nature of the entities in that system and the processes that are taking place in that system. So what is that I call an intuitive assumption? So I'm going to try to demonstrate to you that you have intuitive assumptions that you use to make sense of whatever phenomena you are interacting with. So let me try to do this experiment. I know I'm not there. I would like to be there to ask you questions so that I can get a sense and demonstrate to you that you hold intuitive assumptions. But let's see how it works at a distance. So I'm going to do an experiment with you. It's a visual experiment. I'm showing you on the screen a representation of a yellow ball that I'm going to throw and I'm going to allow to move through a plane. And what you can see there is, I hope, is like a small green screen. And I'm going to do the experiment. And that's what happens. So I'm going to repeat the experiment. So what I'm going to ask you to do, and in fact, I'm going to ask you to do, is to talk to someone for, let's say, 30 seconds to tell me, what do you think is going on? How would you explain what you see there? And because I can see you from here, I'm going to see if you are really talking to someone. So I would really appreciate if you could talk to someone and tell just very briefly, how would you explain what you see?
Yeah, some of you will like to.
Okay, so maybe someone would like to just give us a first explanation. Imagine that you're a student, you see this phenomenon, and
One
you
of
are asked to
the response
explain.
is that it hit a smaller ball which was hidden and a smaller ball moved on.
Okay, so the idea is that there is one ball behind the screen, a small ball that is hit by the big ball. There.
Okay.
Or
Okay.
another one is like it's the same ball, but it's made up of ice, and then that green thing is a heater, so it reduces, and it comes as a spherical thing because it's rolling down.
Okay.
Very good. So we could engage in trying to figure out what is going on, and because I'm the holder of the knowledge, no, of what this reality I could say all of you have a misconception, no. Mm-hmm.
Yeah.
But the reality is that I could analyze all your responses, and my claim is that although your responses may be different, although you may have different ideas of what is going on here, all of those ideas that you express have underlying assumptions about the behavior of the world. So the moment that I say, this is a yellow ball, you apply everything that you know about balls to try to figure out what could be happening here. If I had said, this is a yellow electron, your assumptions may have been different. And then your explanations would have been different. So in general, for example, we know that humans think that balls move in continuous paths, that they persist over time and space. So no one said, oh, suddenly the big ball suddenly by magic transform into the small ball. That is not the type of explanations that we build with the assumptions that we have about the nature of the things we're interacting with the world. So continuity, coherence, persistence are intuitive assumptions that we use to make sense of the things that we observe, for example, when we see the movement of solid objects. In the same way, I could ask you questions about different phenomena. I hope that you can see the phenomena here. Sometimes Zoom doesn't allow the movies to see very clearly. No, but these are very different natural phenomena. And you may know about the scientific explanation of these different phenomena, but if you don't know the scientific explanation, it's likely that the explanations that you build would be based on intuitive assumptions that you have about the behavior of things. So for example, why do some birds fly in a beat pattern? Well, when I ask this question, when educational researchers have asked these questions to different people, it's very common that people that do not know the scientific explanation would say that the bird in front is the leader and the other ones are following it. Mm-hmm. So that is not a correct explanation based on what we know, but it's based on intuitive assumptions that we made about the behavior of the world. Yes. So what we have been trying to explore is what are these intuitive assumptions that our students bring to the chemistry classroom that may interfere with their reasoning when we are trying to make them think about atoms and molecules and chemical bonds, etc. So what we have found in our research is that in general, when we ask students to think about what we call in chemistry structure properties or structure behavior relationships, that means connecting the composition and the structure of substances to their properties and behaviors, they typically manifest four main types of intuitive assumptions that we have given them a name, like inheritance or additivity, centralized causality, and teleology. I'm not going to discuss each of them. I just want to illustrate some of them so that you get a sense of what our research is telling us. So I'm going to focus on these two properties of inheritance and additivity. So again, imagine that I would ask you to explain to me why these feathers are multicolored. Mm-hmm. And again, imagine that you do not know the scientific explanation for this phenomenon. So what is that we observe students doing? And in general, people that do not have the scientific background in this specific area. Well, they rely on common assumptions. One is the assumption of inheritance, that is based on the idea that the properties of the things that we see are related to the properties of the things they are made of. So for example, if you see this copper coin, students or people in general will, and you see that this copper, the copper is reddish, you will assume that the particles that make copper also have that color, so that they inherit the properties, and it's an inheritance that goes in both directions. No? So the particles inherit the properties of the macroscopic entity, or the macroscopic entity inherits the properties of the particles they are made of. So that's a very common assumption made in chemistry classes, no? That the properties of the atoms and the molecules are very similar to the properties of the substances that we see at the macroscopic level. And the other assumption is the assumption of additivity. That is that the properties of the macroscopic object are kind of the weighted average of the properties of its components. So if I see a green leaf, well, I may assume that maybe it's made of molecules or atoms that are a combination of blue with yellow with white. Yes? So the result of what we see is just the average of the properties of the components. Now, these assumptions are very powerful, are very difficult to change, and I will illustrate in the next slide how difficult it may be to change them. But they are very intuitive assumptions that interfere with the learning of chemistry. So we did, for example, several years ago, we did an experiment in which we asked students to predict the color of a chemical product after a chemical reaction. We asked the students to say, okay, imagine that you have a blue substance that reacts with a yellow substance and gives rise to a new product. Can you predict the color of this product? And we asked this question to students in different stages in their preparation in chemistry, entering general chemistry, finishing general chemistry, finishing organic chemistry, that is the second course in the second year in most universities in the United States, entering graduate school in chemistry after 1 year in graduate school in chemistry, yes? And we gave them different options. They could choose that maybe the product is going to be bluish, is going to be green, is going to be yellowish, and the fourth option is that more information was needed to make the decision. And this is what we found. The majority of our students, after completing 2 years of college chemistry, the majority of them, around 70%, still predicted that you could expect the product to be greenish. That is an incorrect assumption because the properties of the chemical compounds are not the properties of the components, of the individual components. The correct answer is more info is needed. But you can see that it takes years for students in chemistry to develop the scientific, the scientific assumption and overcome the intuitive assumption. And we have seen this over and over with the different assumptions that we have investigated. These are assumptions that are very difficult to change. The second type of intuitive reasoning that we have been investigating that also guides and is very powerful in guiding students and people in general, but it's also a constraint in our reasoning, is the application of what we call heuristic reasoning. And the basic idea behind relying on heuristic reasoning is that it allows to reduce the complexity of completing a task. It reduces the cognitive load and it facilitates decision making. So again, I'm going to try to demonstrate to you that you apply reasoning heuristics whenever you are put in a situation in which you have little information to make a decision. So heuristics in this talk refers to fast and frugal mental strategies that we use to make decisions and build inferences. So what I'm going to do is just a very short experiment. Again, please play with me. In this case, I'm not going to ask you to share with anyone. I'm just going to ask you to think what would be your intuitive response if I ask this question. So I'm going to show you 2 containers of milk. Imagine that you go to the supermarket and you have to choose a milk and you have 2 options. I want you to think what is your first response if I ask you to choose between these 2? Which one would you choose? So when I ask this question, most of the people choose the one called latte. Without knowing the difference between this one and this one, for some reason, we tend to, or most people, in particular most people that speak languages that English or Spanish, that are languages in which milk or leche is associated with this, they tend to use this one just based on the simplicity of the name. And I'm going to show you now the image of 2 people, 2 different people, and I'm going to ask you to think in which one would you trust more? Which one would be more trustful from your perspective? And again, when you choose this, most people choose this image, the image to the right. Yes, and the question is why? Why, if we don't know anything about these individuals? So these type of experiments have been done with different people just to demonstrate that all humans engage in heuristic reasoning that allows to make very quick decisions in very little time. So we were very interested to explore if heuristic reasoning was something that was happening in our chemistry classes with our chemistry students and how pervasive it was. So what we did was a variety of experiments in which we asked students to make decisions. For example, we would say, okay, imagine that you want to build a camp burner and you have 2 options for fuel. One is called CH4 and the other one is called CH4O. And they had to make a decision about what would be better and justify it. And our hope was that they would make the decision based on their chemical knowledge. And what we found is that the majority of our students were not making the decision based on their chemical knowledge. They were making the decision based on very fast, quick heuristics that they would apply to make the decision. And I'm going to illustrate how they typically did it. So when confronting the basic idea of heuristic reasoning is that whenever we confronting making a decision with little information to make the decision, our mind does these three main things. One is focuses on the most salient differentiating feature of the two things that we have to decide from. So in this case, most students would focus on the fact that the formula on the right has an O and the formula on the left doesn't have an O. So that was the first thing that was salient to them. Second, they would associate that difference using implicit assumptions to try to answer the question. So they would say things like, for example, okay, I know that O is oxygen. I know that oxygen is involved in combustion. Well, maybe that makes this substance the most useful for building a burner because it would be better because it would burn better. So they would use this intuitive knowledge to make the claim without necessarily relying on their chemical knowledge. That would have led them to use the other one as the best fuel because it's the one that has a higher heat of combustion, for example. So in general, when we engage in heuristic reasoning, what we do is instead of answering the question that we are asked to answer, we answer a different question. No? For example, my students didn't answer this question. The majority of them, what they answer is the question is, which of these two have oxygen? Not which of these is the best fuel. So when this happens, what we observe is that when students engage in heuristic reasoning, instead of engaging in causal reasoning, what they do is just build simple associations and engage in what we call relational reasoning. We have done a variety of students in this area. We have identified typical heuristics that our students use. They typically engage in recognition. They base decisions on similarities between the properties of substances that they know and they don't know. And they tend to reduce their decision making to identify one single cause for explaining what is going on. So just to illustrate how this works, well, before I illustrate that, so in general, what we have learned is that whenever we work with our students to try to understand how they reason, what they tend to use is intuitive assumptions that serve as a blueprint to guide their thinking. Then they bring whatever pieces of knowledge they have acquired in our classrooms. And then they use heuristics to combine these assumptions and this knowledge to build different type of explanations that sometimes are appropriate, but sometimes you can think of them as monsters. No, from the perspective of from a scientific perspective, they seem like irrational ways of thinking, but they result from the combination of these intuitive assumptions with pieces of chemical knowledge that they have acquired in their classrooms, and with this engagement in heuristic reasoning that tends to reduce the complexity of the factors they have to pay attention to make decisions or to build explanations. As I said, we have done some studies. Not only at college level. This study was done by Dr. Patricia Moreira. She's from Chile. She worked with the students in 10th grade, and she asked them to explain how they thought that antifreezers work. And what she found is, again, that most of the explanations that the students built could be classified into main groups. One that was guided by the additivity assumption with and heuristic reasoning that was what we call the one reason decision making. So they would identify a difference. They would say, oh, what happens is that the antifreezer has a different melting point than water. And when they mix, the properties of the mixture are the properties of the combination of those two. So that was a typical additivity assumption with a one reason decision making. And the more sophisticated ones would engage in some sort of causal reasoning. But again, they would have certain assumptions about, for example, the idea that that the behavior of systems is guided by entities that have certain goals. So for example, in this case, they would say that the alcohol that serves as a coolant or as an antifreezer would prevent the water from freezing. So it would have like an active agent that is controlling the behavior of something else. That is also a very common assumption when we think about the behavior of chemical substances. So in general, what I just wanted to show with this in this part of my talk is that what we have found is that when you do studies with the students that have completed traditional chemistry courses, by the end of the courses, the reasoning that they manifest is far from the reasoning we would like them to have developed. So just to give you a sense of what is typical that we see, this is a distribution of the responses in this particular study that Patricia completed, but it's very common in other studies that we have observed. The majority of the students engage in non-causal reasoning using associations, relational reasoning. Very few engage in mechanistic reasoning, even after completing our traditional chemistry courses. So based on this research, we decided that we needed to do something in our own classrooms to see if we could help students to better develop the type of reasoning that we value. So we engaged in educational reform. And what we did is said, if we are going to change based on our research and the research of other individuals, what we need to do is to think not only on changing the instructional strategies that we are using, but we also need to change what are we teaching, that means the content, the curriculum, and how we are assessing the student understanding. So we engage in a large and major reform process, but we didn't do it in a single step. So I will show you a little bit later what is the story of the project, but we started in 2007, and we still continue doing changes in different areas to try to improve the learning outcomes and the performance of our students. So what we did is to develop a relatively complex educational framework in which we ask the questions of, okay, what is to be learned and what for purpose? So we pose different questions, no? What learning dimensions are we going to target? What ways of reasoning we want to foster? How we are going to organize the content so that based on what we know, based on educational research, we know how to best help students progress in their understanding, etc. We also ask questions related to how we were going to organize the content, what learning anchors we were going to use, what type of interactions we would like to foster in the classroom. And we also ask questions about assessment, how we were going to elicit our students' understanding, how we were going to interpret their ideas based on particularly when we work with hundreds of students in the classroom, how we were going to change our assessment. So what I want to do is very quickly tell you a little bit of what type of changes we have implemented. So first, in terms of dimensions, we said that we wanted to get rid of this idea that you come to a chemistry classroom just to learn chemical knowledge. We wanted our students to understand that chemistry is a way of thinking, it's a way of knowing, and it's a way of acting. So that we had to move beyond just presenting content to engage actually students in doing chemistry, not only doing chemistry with their hands, but doing chemistry with their head. We also wanted to explicitly focus on the type of reasoning that we had investigated. So we focus right now, our curriculum focuses on developing mechanistic reasoning, helping students to use science practices to make sense of phenomena in the real world, and then using that knowledge to engage in systems thinking so that they can engage in sustainable decision making. So very explicitly, we said what type of reasoning we want our students to develop. We have changed the way we conceptualize the curriculum. The curriculum in chemistry and in many scientific disciplines is organized around topics. For example, this would be a typical organization in chemistry, talking about atoms, molecules, interactions, reactions. We have gotten rid of this structure. What we do now is to organize our curriculum around questions. So what we do is we pose a question that we want our students to grapple with, to understand that chemistry allows us to answer this question in different relevant contexts. And we bring ideas and concepts that are needed to answer that question as needed, given the problems that we are dealing with. So we had to develop our own materials, our own educational materials. The curriculum is called Chemical Thinking. Just to give you a sense of what questions we pose and work with our students in the classroom, the first unit is focused on trying to answer the questions, how do we distinguish substances? And the image that you see here in the middle, is illustrating that the context is understanding what substances are in our environment, for example, in our atmosphere. Then we move to how do we determine structure, and the context is how do we determine the structure of substances that are present in our body. Then we will study how do we predict the properties of materials. In this case, we focus on materials of use in our world, etc. So we work through questions, instead of topics, and we engage, for example, in this case, and we analyze chemical processes in the atmosphere. So this illustrates how we have moved to questions. We are also organizing the curriculum with very careful learning progressions. We engage students in the classroom in solving problems by using a learning anchor. A learning anchor is a problem that the students need to grapple with. They need to apply central concepts and ideas, use scientific practices, and engage in sense and making and decision making. And then, let me just skip that. We have changed the format of our classrooms so that the students can interact and collaborate, so that we facilitate interaction with the students. We create many opportunities for the students to make their thinking visible. And because we work in very large classrooms with many students, we use instructional teams where we use the students that have completed the course to help other students learn while they are working in classroom activities. And finally, we have changed the evaluation system so that the students now are asked to complete assessments in which they show that they can integrate central ideas, practices, and ways of reasoning in the analysis of relevant problems. If you are interested in seeing some of our assessments are available online. So you can see all of them are contextualized. They are based on central topics. I assume that my time is up, or
yeah, we
is that
need
correct?
to wrap up.
Yeah.
Minutes you could.
Yeah. So just 1 minute, just to show that we have made different type of studies to show that the progress of our students. I just wanted to show you that we have shown that our students are doing better in standardized assessments. They are doing better in other chemistry courses. We have been able to reduce the failure rate by 20% points. We have demonstrated that they have better attitudes toward chemistry. And we have compared the results of our students, of the performance of our students in our university with the students in other universities. And we have demonstrated that they have better ways of thinking, better reasoning, and they are more productive when engaging in collaboration. And with that, I'm going to stop because I don't want to, and I will be happy to answer any questions that you may have. I also want to just acknowledge the people that have worked with me over the years, and thank you very much.
Thank you, Professor Talanquer. Yeah, there is a lot of excitement and questions, so we'll get going.
Thank you for, I don't know whether you can see me.
I can hear you very well.
Yeah, thank you for a very insightful talk. One of the questions I had was how did you approach training the teachers and other instructors in the university when you wanted to go through this reform?
Yeah, so
What kind of
yeah, that's
resources and training was given?
yeah. So what we did is we started very small. So when we started with the pilot section. I worked only with one other instructor. Then we extended to 2 or 3 instructors, and then we extended to all of the instructors. And the way we did it is by having weekly meetings in which we were discussing the implementation, different changes in the curriculum. And since then, we have continued working as a team. So we work as a team. We develop assessments as a team. So it has been a long process. As I said, we started in 2007. So the process of training the instructors has been not a process that was done and then we were completed. No, it has been a continuous process, and we have been lucky in maintaining the same instructors over the years.
Okay. Hi, am I audible?
Yeah.
Yes.
Yeah.
So thank you for the talk again. So I have 2 questions basically. The first question is, what were your assessment tools for assessing the student performances?
Yeah, so when we started, we used in the United States, it's very common that the general chemistry students are assessed using a standardized assessment. And that's what we used first, because we wanted to demonstrate that despite the changes that we were doing, students were also were performing at least at the same level or better than students that were in traditional courses. And then we have developed our own tools because we are changing the nature of the things we want the students to focus. So we have developed our own assessment instruments to measure mechanistic reasoning, more recently to measure systems thinking. But we started by providing what is called traditional evidence by looking at overall performance in the course, measure behavior in standardized assessments. We use instruments that are available that measure attitudes towards chemistry, for example. So we use instruments that were already there and that had been used in the evaluation of traditional courses.
Okay, yeah, thank you. And the second one was you showed that you have few developed modules from the university. So does that modules cover all the fundamentals necessary for the course or whatever level, UG level or university level they are? All the modules, does that cover the fundamentals as well?
Yeah, so that's a good question because I would claim that the curriculum cover all the same central ideas that the traditional curriculum. That doesn't mean it covers all the content, because I think that many of the content in traditional courses is not central. So we have reduced the amount of content that we cover, but I would claim that without sacrificing the students' understanding of the central ideas in the discipline.
Yeah, so good morning, Professor. So my question is about the 3D learning. So under scientific practices, how will you develop the computational and mathematical thinking in chemistry?
Yeah, well, so the course is very conceptual, but we also engage the students in, of course, in the analysis of on developing quantitative reasoning. The way we do it is by being very systematic in the organization of an instructional task. Our instructional tasks always begin with the analysis of quantitative data that exists for the problem that we are analyzing. Then we engage students in some sort of modeling, and that modeling is both qualitative and quantitative. And then we engage the students in the application of those quantitative models to make predictions about the behavior of the system. So we have these focus on data analysis, modeling, quantitative modeling, and then application of those models to make quantitative predictions. So those are the 3 basic quantitative skills that we try to target over and over in all the instructional tasks that we develop.
Thanks. Thank you.
Okay.
Yeah, I agree with your assessment that one of the main problems in teaching chemistry is that questioning is not a focus of the teaching. In fact, I remember when I was first learning organic chemistry in university, I had a huge problem that there was no space or time to really ask, why are these reactions occurring? Now, there's some of us here at, who a few years ago here at Homi Bhabha Center who were doing research on student questioning. And what we think is that what is really needed is that the students themselves, in order to learn, the students need to be the ones asking questions. And we found that just because teachers or textbooks are posing questions doesn't necessarily mean that students are posing questions. So have you looked at this, whether students themselves are posing questions?
Well, at this moment, the curriculum is very, I mean, the questions that are posed, the main questions that are guiding the discussions in the classroom are posed by the curriculum and by the instructors. But the students work on these activities in small groups. And during those in those discussions, we encourage the students to ask their own questions and pursue their own ideas. But you're right. At this moment, the curriculum as it exists doesn't create a lot of opening, no, for the students to have a lot of agency on the definition of what questions they want to pursue. So it is not ideal. No, at the level of agency, I would say that this curriculum is still providing little opportunities for students to pursue their own questions.
Yeah.
I have a question, which is, I come from a background in mathematics education, and invariably you need to allow certain amount of confused reasoning before clear reasoning emerges, right? And when students are learning. Now, with individual learners, you can scaffold and you can help a lot. But when you're doing it on the scale and there is collaborative one, there is also the problems of confusing each other and leading people down a different path. So how, with this scale, how do you manage looking at that?
Yeah, so that's what we work with instructional teams. It's not a single instructor. We have what we call learning assistants or preceptors that are students that have completed the course. And so depending on the size of the classroom, for example, in my classroom that has 200 students, I have around 10 to 15 preceptors. So those preceptors, while the students are working in groups, they walk around, they listen to the conversations, they intervene to clarify or to guide the discussions when needed. No, but we try to provide as much individualized guidance, well, not individualized, but at least group guidance. No, when we are constantly posing questions to the groups to get a sense of eliciting their ideas. We orchestrate these classroom discussions to try to direct students' thinking in the way that we think that is appropriate depending on the nature of the task. It is challenging, I have to admit it. I don't think that we are 100% effective. But what we have tried and we have had some success is by using these instructional teams to ensure. We also use a lot of technology so that the students individually can provide their own answers to questions, like by using response systems. That allows to monitor the level of confusion to a certain extent that exists in the classroom. So we are trying to use a variety of human and technological resources to gather as much data as we can in the classroom to guide what we are doing.
Thanks. Yeah. Good.
Thank you, Vicente, for a nice talk and inspiring ideas on teaching and learning. My name is Urban Eriksson. I'm a professor at Uppsala University in Sweden. And my question to you is, you have worked a long time with this. And since the audience here is not just chemists, teachers, does this apply also to biology, physics, astronomy, etc.? Have you tried that, or has any of your colleagues that you know of tried that? And what would then that result be?
Yeah, so in terms of research, this idea of intuitive assumptions and heuristics, there is people that have done research in biology and astronomy too, and I mean we know that that is common across scientific disciplines. In terms of curriculum reform, I don't know. I'm not familiar with change with this level of change in the curricular approach. In the curricular approach, of course, there is a lot of work on engaging in active learning and collaborative learning, but the change at the curricular level, I am not familiar in biology or physics to the extent that we have done it. But I do believe that it would be good and it would be possible to organize curriculum, for example, around essential questions instead of topics. Use a similar framework to think about. Of course, the three-dimensional learning in the United States is trying to be implemented across different areas, so there are many people working in that direction. So I think that there are components that can be found and have been demonstrated that can be successful in other areas, but I think that in other areas maybe the curriculum that I'm presenting is not common across other disciplines.
Thanks, Shweta.
Yeah. Hello. My question is a methodological one. So we are also trying to work in a settings where there is a collaborative student setup and trying to analyze the reasoning. And we have facing so many challenges. So I wanted to understand how do you, because you spoke so much about reasoning heuristics and mechanistic reasoning. How do you do that, analyze that in a collaborative setting? There are multiple voices.
Yeah, so I didn't have time to talk about this last study. This is a study was done in classrooms, and what we did is by videotaping the conversations of the students in different groups, and we analyzed those conversations to see what type of reasoning was manifested in these collaborative spaces, who was participating, what level of knowledge sharing versus knowledge construction was taking place in these collaborative groups. So it was challenging. It is difficult because what we realize is that every group is a different world, no? And even when you are working on the same task works in different ways in different groups, depending on the composition of the groups, the background knowledge of the students in the group, the motivation of the students in that particular group, in that particular day, or in that particular moment of the classroom. So it is a very challenging enterprise. I always say that teaching is very complex. So what we have learned is that we are successful, but we are not successful in all of the groups with all of the tasks at all times.
Yeah, I think there are a lot of excitement and questions, but I think due to time, we need to conclude this session. I really thank all of you for your questions and ideas, and I really thank Professor Talanquer for giving this time and sharing his work with us. It's really valuable for many of us who have been struggling with this, both as a chemistry educator, but also science educator in different dimensions. So I feel your sharing will be valuable. Maybe some of us can also continue the conversation online with over emails with Professor Talanquer. He has shared it. With this, I would like to conclude this session. Thank you, Professor Talanquer, and thank you all for listening.
Thank you.
So we take a brief tea break and we get back for the next session by 10.